Good afternoon, everyone. My name is K.D. Singh. I am a solutions architect with Amazon Web Services. This session is about big data and analytics on AWS. It's right after lunch. Hopefully you had coffee. So I am going to present this session along with Marco Merens. Marco is the head of analytics of International Civil Aviation Organization. Came here from Montreal. So we'll divide up the session. In the first part of the session, my goal is to give you an overview of the big data field, tell you more about the AWS services related to big data, sort of give you an idea of how to architect a big data solution, and then give you a real world example of how to put these different blocks together to build a real world pipeline on big data. And I have 30 minutes for that. So I can't go down in the weeds, but I don't want this to be marketing exercise either. So hopefully you're going to find this useful. AWS training actually has a 3-day big data training that covers all these topics in much more detail for those of you who are interested. After I'm done, in about 30 minutes, Marco is going to come up and he's going to show how his agency was able to use AWS services to solve their big data problem. And then I have a demo. It's a 6-minute video. After Marco is done, if we have time, I'm going to play that demo and it's going to show you how I put these services together to build something useful. So let's get started. Okay, so big data is no longer a buzzword. It used to be that big data this and big data that, but now pretty much everybody knows that there is a great amount of value in data. Nobody is throwing away their data anymore. People know that in that data is hidden lots of useful information and knowledge that can help in their decision making, to do things more efficiently, to save money, to do a lot of different kinds of things. So, and when we talk about big data, many of us have heard about the 3 V's of big data, like the volume of big data, how big it is, the velocity of big data, how quickly is the data changing, the variety of data, how many different types of data are bundled together in my data store. But there are other parameters. On this slide, you see some of the parameters that help define the problem space. But the bottom line is, big data is different things to different people. People think about, what really is big data? Is a gigabyte big data, a terabyte big data, a petabyte big data, exabyte big data? The real answer is that any or all of that could be big data. It just depends. If you're talking about sensors in the field, in scientific computing, in the federal space, NASA and all, where the compute power is limited, even megabytes could be big data because you don't have the processing power. And when you're talking about cloud scale things, people have exabytes worth of data in there. The bottom line is, anytime you have to think about or redesign how you are accessing your data, how you're storing your data, how your analysis works, and how you're visualizing your data, anytime you have to change that, you're probably dealing with a big data problem. And for those of us who know this space, there are just a lot of tools in the ecosystem. This is just a very, very small sampling. There are hundreds, if not thousands, of tools in the ecosystem. And when somebody first gets introduced to the field, the first challenge is, how do I break this up? How do I even think about, hey, should I be looking at Dynamo or should I be looking at Cassandra? What is Cassandra? Where do I go? What is a data warehouse? What is Hive? What is Pig? What's the difference? What is MapReduce? There are just too many things. And to make things a little bit simpler, to put some structure around it, I think it's best if we think of big data processing as a pipeline of things or stages that you have to go through to solve your problem. The different stages in the pipeline are okay. So on the left, you have your incoming data, and on the right, you have your answers in this particular pipeline. The very first thing that you need to do is to ingest your data. You have to consume it. after your data is in your hands, you have ingested it, you then have to store it. After you store it, you analyze it, you process on it. And this is an iterative process. When you analyze something, you have to store the partial results back. You want to keep your data for longer. So storage and analysis, it's iterative. There is a feedback loop in there. And finally, after the analysis is done, then comes the part of visualization of data. You have to see the results in some way, shape, or form. When you see results, you might have to go back and analyze again, change some parameter again. So it's an iterative process as well. But the bottom line is ingestion, storage, analysis, and visualization. Almost all big data pipelines can be broken down like this. You might have some other components. You might have fewer components than this, but this is like the de facto starting point of when somebody like me starts architecting a big data solution. This is how we break down things. Now that we have broken down things, we can, all the tools, the NASCAR slide we saw about the big data tools, we can now make it a little bit more structured. So now we have 4 buckets in which we can throw things. We have the ingestion bucket, the storage bucket, the analysis bucket, and the visualization buckets. And now these tools, they line up in one of those buckets. There are some that span different things, but more or less, these are the 4 different buckets in which you throw things. Now you can break up the problem and start looking at the choices within a particular bucket. There are still a lot of tools, hundreds or thousands, as I said. So in this talk, what I'm going to do is look at the managed services that Amazon Web Services provides that deal with big data kind of problems. And these are the services that I'm going to, I can't go through all of them, 30 minutes. And 50 Amazon services, or close to 50 Amazon services, so can't spend too much time on them. I'm going to cover a few of these services related to these topics. This is my only marketing slide, I promise. Just shows you who is using big data. If you're wondering whether this is relevant for me or not, it probably is, because a lot of different kinds of customers doing a lot of different kinds of things, chalk and cheese kind of things, they all use big data kind of solutions, and draw really good value out of it as well. So now let's start looking at those 4 stages of pipeline one by one, and then we'll start looking at some of the technical details in them. In ingestion, the idea is I have to consume the data. So what are the different kinds of data that you might have to consume? That's going to then tell you what kind of tools you need to solve that problem. Your data could be transaction kind of data, database reads and writes, sequential database reads and writes kind of data, transactional. And then it could be file kind of data. You have media files, you have log files, simple files, could be document files or anything. And finally, there could be stream kind of data. Stream type of data is the most challenging data to deal with because it's real time. The streams never stop coming. Twitter feeds, people tweet a lot. That data does not stop. There is a lot of value out of that you can derive out of social media feeds like that. Things like sensor data, Internet of Things, the fridge talking to the TV. There is just a lot of data that's going to get generated, and it's getting generated. That kind of data is never ending. So ingestion of streams is not an easy problem to solve. So in this session, I'm going to talk about Amazon Kinesis, which is a service that deals with stream processing or ingestion of streams of data. So let's look at that. Okay, Amazon Kinesis, it's a fully managed service. Before I start talking about Amazon service, the first thing I'm going to say is that anything that Amazon is offering as a managed service, whether it's Elastic MapReduce or Redshift or DynamoDB or anything, you can set up equivalent services on your own. You can, of course, do that. You can launch, I'm assuming all of you know what EC2 is, what S3 is, what ELB is. You can use those different services to come up with your own services, the fundamental services to build up higher level services. And you can also use the open source tools in the ecosystem or partner ISV tools as well. The reason I like the managed services like Kinesis that I'm going to talk about is that it takes care of the undifferentiated heavy lifting. If I'm managing a project, my mission is not to set up a cluster. My mission is to derive the analysis and the useful information out of it. So, managed services take care of those kinds of undifferentiated heavy lifting, so I like them. But if there is some feature that a service is missing, you can always launch your own service or use something from the ecosystem or a partner. So Kinesis is a managed service. You fire it, and it handles a lot of things for you. It is in the real-time data processing field. You can, when you use Kinesis, the key idea is you set up Kinesis streams. A Kinesis stream, when you set it up, you can put records in it. Records are blobs of data. Kinesis stream, you put records in it. What Kinesis is going to do is, it's going to keep the records that you give to Kinesis around for 24 hours. It's going to order those records and put them around safely for 24 hours. Within those 24 hours, your application, the next stage of the pipeline, which is the storage or analysis, is going to come in, get the data out of the records, and work on it. And after that, you can either throw the data away, or you can store it in a more durable storage like S3. But Kinesis, it gives you enough capacity so that you don't lose any data. Data is coming fast. What you do in Kinesis is you set up shards. A shard in Kinesis, a Kinesis shard, can consume data at 1 megabyte per second, and it can emit data at 2 megabytes per second. So, and if you need more throughput than that, your data is moving faster than that, you just provision more shards. So you provision the number of shards that you need to input all your data. All the records are in there. Kinesis offers what we call different libraries. You can use the APIs directly, but there are libraries, the producer library, connector library, and the client library from Kinesis. You can use those libraries to write applications that consumes data from records, or that put data as records, or that connect to other durable stores like DynamoDB, S3, or Redshift. The cool thing about using Amazon Managed Services is that they all talk to each other very well, so it's very seamless. But to recap, you have a stream of data, records are coming in, shards are consuming that data, and data is kept around for 24 hours. You consume data in those 24 hours and either discard it from Kinesis or put it in a durable storage. So using that, you can get sensor or real-time data very easily. And Kinesis, there are actually other tools in the ecosystem for those of us who deal with this field, things like extract, transform, and load. ETL kind of things are closely related to ingestion. That's when you do ETL, when you ingest things in. So a lot of partner tools, BI tools, and tools from ISVs, they work very well with Kinesis, and you can leverage them as well. So let's go to the next stage in the pipeline. The next stage is storage. Before I start talking about storage services, I'm going to talk about an anti-pattern. So it used to be, till some years ago, that companies used to have a relational database data store, which is RDBMS of some kind. People have their favorite, and then that used to be their source of truth, their data lake. Every kind of data used to go in that store, and so it was like a Swiss Army knife, but it was an unwieldy Swiss Army knife, because those of us who know databases, we know that they are a pain after some time. They have been around for a long time, and people know them really well. There is a reason why NoSQL stores also let you write SQL queries for the most part, because SQL is really well known and used, and I'm a big fan of using relational databases as long as they can satisfy my needs, but they are not a good match for everything. And people were trying to use them for that, and then they dealt with things like, hey, scaling. How do I scale it? Let me shard it, or let me reindex it, and it was painful. So that's why what started happening is that it's better if you think about what kind of data are you trying to store. Not all data is created equal, and not all data has the same kind of requirements on the store where it's sitting. There are different kinds of data that you are dealing with. There is caching kind of data for those of you who use Memcached or Redis to speed up your data stores or key value stores. There is caching kind of data. There is file store kind of data or blob data. There is key value stores or document stores which fall in the NoSQL kind of space. And there is archival kind of data, and there are file system kinds of data stores as well. I mentioned Hadoop distributed file system because that's part of the Hadoop ecosystem that I'm going to talk about, but there could be others. Storage should match data's needs. There is search kind of data as well, which is also very popular in the big data space. So once you break up your data storage needs like this, now you can try to match the right service that would handle that kind of need. If you are just storing files, if it's just blob data, why do you need to put it in a relational data store? You can just put it in something like S3. If it's archival, hey, you don't put it in relational databases at all. You put it in Glacier or something like an archival service like it. Similarly, for caching, so these are Amazon services that correspond to those kinds of data storage needs. We have RDS, which is the relational data store service. It gives you relational databases. I'm going to talk about that. DynamoDB is NoSQL data store. I'm going to talk about that. EMR or Elastic MapReduce is managed Hadoop clusters, etc. So let's look at some of these storage services. S3, simple storage service. I'm pretty sure almost all, if not all of you know what S3 is. I'm not going to spend too much time on it, but it's an object store, which is it scales very well. It's very durable. It's designed for 11 nines of durability, but more importantly, it has some key features that make it very useful for the big data space, which is what we are focusing on. Features like versioning and lifecycle management. So once you bring your data in, you can version it, and then you can write lifecycle policies so that data transitions into Glacier after some time. It has things like security is important, so encryption of data at rest as well as in transit. It's a feature that you can leverage from S3. And then it has event notifications as well. So when some new data comes into S3, you can get notified using SQS, Simple Queuing Service, SNS, Simple Notification Service, or using Lambda events. Lambda is another cool service. I don't have time to cover it today. But it means that when data comes in, you can kickstart new things. So your pipeline can be more automatic that way. So S3, I've been an architect with Amazon for around 3 years now. I've designed hundreds of architectures. I've still not designed any solution that did not have S3 in it. It's just like very useful in a lot of different scenarios, including big data. Okay, so let's look at DynamoDB. DynamoDB is a fully managed NoSQL service. Again, it's managed for you. What is managed is things like, thank you. So, yes, okay, here I am, okay. Got ahead of myself, okay. So, what is managed for you in this NoSQL service is the underlying infrastructure, the software on it, the patching of it, the scaling of infrastructure when you're throwing more data at it, the patching of the software, as well as sharding or whatever is required behind the scene. It's managed for you. You just give it your data. It's bottomless. You provision the amount of throughput you need, and you get it. It is useful for both key value kind of data as well as document kind of data. I normally like to keep it more interactive, but in this kind of scenario, that's not possible. But the key idea of a key value store is that when you have some data in which you can you can divide up into key and value. This is my data element, this is the key, and this is the corresponding value. When I give you the key, give me back the data or the value. That's the key notion of a key value store, and a lot of data out there is just like that. And document store is things like if you have to do some storing, querying, or updating of documents in XML, JSON, or XML format. That's when, or HTML, that's when document stores become important. And DynamoDB is a data store that handles both key value stores as well as NoSQL stores. In 30 seconds, the key idea of a NoSQL store is that most relational databases are ACID compliance. So they offer a lot of functionality and full SQL kind of compatibility, but in a lot of circumstances, you don't really need that full SQL kind of capacity. You don't need to write all kinds of SQL commands, and you don't need full ACID compliance unless you're doing financial transactions, etc. In those cases, it makes a ton of sense to use a NoSQL data store, which scales very easily and to a really big extent over and above what a relational data store can do. So that's where stores like DynamoDB come into picture, and there are others in the space. There are probably more than 100 NoSQL stores out there like Cassandra and Mongo that you can set up on Amazon as well. DynamoDB is just managed for you. Real quick, some key terms related to DynamoDB. It has tables as well. Just like in relational data stores, there are tables. But instead of rows that we have in relational data stores, in Dynamo we call them items. Each row is an item. Each item has attributes. Instead of column values, we have attributes within an item, a bunch of attributes combined together to give you one item. An item can be up to 400 kilobyte in size. That's the limit. But you can have as many attributes as you want, and different items can have different number of attributes. So there is no real schema. It's very, very flexible. All you need to do is specify one primary key. Once you have that primary key, which uniquely identifies an item across your table, the rest of it is very flexible. So you can throw a lot of different kinds of data in there. So I want to reiterate that relational databases still have a place in big data space. I'm a big fan of keep using relational databases simply because they have been around for years and years. A lot of people have expertise on them, and they are known to work well. Unless you're feeling pain around it or your data sizes are not that big or not scaling or changing very fast, relational databases do have a place in this space. RDS, Relational Database Service, is a managed service from Amazon. It offers you choice of 5 different database engines. You can choose between MySQL, PostgreSQL, Microsoft SQL Server, Oracle, and Aurora, which is a homegrown kind of engine. Aurora is actually MySQL compatible, but they have done some unique engineering which makes it scale much faster and perform much better than vanilla MySQL would do. With RDS, you can provision these databases, or RDS can provision these kinds of databases for you and do a lot of low-level things like patching or backups or snapshots or launching databases in multi-AZ for failover kind of things. They are managed for you. So RDS is a cool service as well. So let's look at the next stage, which is around processing and analysis. Okay, I don't know how to go back, but there are 2 kinds of processing frameworks. There is batch processing and there is stream processing. The key idea of a batch processing framework is that you are working in batches. You have some cold data, you chunk it up together, maybe in terabytes worth of data, and you work on it together. And the results, they can come back in minutes or maybe hours. It does not really matter. You are working batch by batch. And a good example of batch processing kind of workloads is when you are creating daily, weekly, or monthly reports. That's typically when you are doing batch processing. Stream processing is real time. It's like the stream ingestion that we were talking about, that you have to work in pseudo real time. you want results back in seconds. So you can't really chunk up a lot of data. It's hot data, it's changing very fast. And a good example of stream processing is 1 minute metrics, when you have to find some log information or clickstream analysis or bidding, or lots of applications want your processing to be really fast, and that's where stream processing frameworks come into picture. And this slide shows you some of the tools in the ecosystem for batch processing kind of workloads, and this is where I'm going to focus today. We have Redshift, which is a data warehousing solution. I'm going to get into what data warehouses are. We have Elastic MapReduce or EMR. And then there are a lot of tools in the ecosystem. In the Hadoop ecosystem, there is Pig and Hive and Presto and Pala. There is Spark, Spark streaming. There are a ton of things there. And for stream processing, we have open source tools like Apache Storm project. We have Spark streaming. And then we have, with Kinesis, there comes the Kinesis client library. So you can write your processing application using KCL as well. So I'm not going to focus on Kinesis because we talked about it already. Next, I'm going to talk about Redshift and EMR. Okay. Data warehouses, the key idea of a Amazon Redshift, it offers you a fully managed data warehousing solution. It's a columnar store. The key difference between a relational database store, which under many circumstances many people are using as their warehouses as well, which is fine. But when we are talking about enterprise scale data warehouses which scale to terabyte or petabytes size data, your relational data stores no longer cut it. So all the good enterprise data warehouses out there are columnar data stores for the most part. And they are typically used for OLAP or online analytic processing as opposed to OLTP or online transaction processing, for which relational data stores are mainly used. They are columnar data store, which essentially means that when the data in your tables is stored on the storage device, say a hard drive, it's stored column by column. A relational database would typically store data row by row instead of column by column. Storing data column-wise makes sense in analytic processing kind of workloads because the kind of queries, both use SQL, by the way, both can use SQL, but the kind of queries that you write against them are different. Analysis queries, an example is things like for the United States, in the state of Virginia, in the district of Fairfax, find all the citizens who are women between age this and this, which means that you have to scan the whole column to find that piece of information because that's how data is typically laid out in a table. If the data is stored column by column, when you're consuming or reading data from the data store, the block that you get back would have all that information in one go and you can easily process on it. If it's row by row, you'll just have to read a lot of data just to get to the information you're trying to get to in the analytic pipelines. So that's why relational data warehouses are typically columnar store. And Redshift is, as you know, it also has some other very cool features. Things like it has a massively parallel pipeline. When you launch Redshift, you're essentially launching a cluster. You're actually launching a cluster with a leader node and child nodes. And when you write a SQL query, it gets mapped into things that each of these children nodes do in parallel. So it's a cluster of things trying to run your query in parallel. And then it does compression of your data. When you store data column by column, as you can imagine, data sitting next to each other is all of the same kind. If it's int, it's int. If it's string, it's string. Unlike in row where things can mix and match, in a column they are all of the same kind. So compressing data becomes much more easier. So you can get 3x, 5x kind of compression. So that way, when you read the data back, with a single read, you get a lot of data back in the same read. So these kinds of optimizations make Redshift go really fast. So it's great tool for batch processing kind of things. People do nightly writes to it, and then they write their analytic queries against Redshift. It comes in two different flavors. there is dense storage nodes in Redshift, and there is dense compute nodes in Redshift. Dense storage nodes are hard drive based, and they scale up to 1.6 petabyte in one cluster, in one Redshift cluster, and then you can have multiple Redshift clusters as well. So we are talking about really big sizes here. And dense compute, they just have a lot of RAM and latest generation processors, as well as SSD drives. So they compute really fast. So the results come back much faster. So you can choose either or. But the bottom line is, data warehouses, the main problem is they are great, but they are very costly. Redshift solves that problem. You can start at 25 cents an hour, and then you can get to the rates like $1,000 per terabyte per year. And if you know about data warehouses, their licenses can run in 6 figures. So it just levels the playing field a lot. And a piece of trivia: Redshift is the fastest growing AWS service. Since its launch, it's the fastest growing. Lots of need for it. All right, so let's look at MapReduce briefly. So Elastic MapReduce, or EMR, it enables businesses, researchers, data analysts, all kinds of users to easily and cost-effectively process a lot of data, which might be unstructured. We have not talked about unstructured versus structured data, but a lot of different kinds of data using commodity hardware. It actually, behind the scene, uses stock Apache Hadoop project implementation. There are partner implementations from companies as well, like MapR, but the EMR service by default gives you stock Apache Hadoop things. And the Apache Hadoop, it's a distributed data processing engine. And distributed data processing engine, it's Java based. And the key idea there is something called MapReduce. The notion of MapReduce is you divide your data up into many small fragments that can be worked on in parallel. So you break up your problem into 2 stages. The first stage is called map, and the second stage is called reduce. I don't have too much time, but the hello world example of this space is the word count kind of example. The idea is you have thousands or maybe millions of files, and you are trying to count how many times a particular word appears across all of them. The first thing that you can think about is that, hey, I don't need a single compute node to work serially along those files. I can divide up each, say if I have 10 files and 10 different compute nodes, I can have one compute node and look at each file and then determine how many words are there in that file of a particular kind, like how many times the appears or how many times Washington DC appears, etc. And then I have to add them all up to come up with the final number. But the bottom line is initial processing is all parallel, it's all independent. And that's the key idea of MapReduce. You divide up your problem to have 2 stages, map stage in which things can all happen in parallel. So Hadoop clusters can span thousands of nodes as well, and lots and lots of data can be consumed by it. And then there is the reduce stage in which the final results are accumulated across all the different nodes. And EMR implements that very nicely. And here is a typical design pattern of how EMR works. Your input data is in S3. You launch an EMR cluster. In the end, when I play my demo after Marco is done, you'll see EMR in action a little bit. But you launch the cluster, tell the number of nodes you want. You tell using Bootstrap steps what kind of software you want on it. Your software can include all the popular things in the ecosystem, including Hive and Pig and Impala, etc. EMR installs them for you, Ganglia, etc. And then you write your mapper or reducer. You can use the map and reduce codes in the ecosystem as well. And finally, your results come back to S3. So that's one pattern. But you can do things like you can resize your cluster very easily. You started with 5 compute nodes. Hey, It's a parallel application. I can add more nodes and get done quickly. So add more nodes, and EMR resizes things for you. It works very well with spot pricing. For those of you who know spot pricing, you bid against unused AWS capacity. Behind the scene, EMR is using EC2 and S3. Those are the services it's leveraging. It's transparent about it. So it can bid on your behalf on unused capacity and use spot pricing very well to optimize on costs. And again, it works very well with a lot of tools in the ecosystem. The last part of my talk is about visualization. Amazon does not have any service in this space simply because the partners and the ISVs that we have, there are a lot of tools out there that people already use and love a lot, and all of those tools work very well. They work very well because things like Redshift, they expose standard JDBC and ODBC connectors to which all of these tools can talk to. So there is nothing proprietary there. So the ecosystem is very rich. You can use any of the tools. In my demo, I'm showing how to use Pantaho, which I just started using, but you can use Tableau or Jaspersoft or any other tools that you like as well. And this is my final slide before Marco comes in. And in this, I'm just putting everything back together. So we started with a lot of different tools in the ecosystem. And then we said, let's create a pipeline with different stages. We looked at ingestion, part of pipeline, and there are several tools in it. We looked at that data could be transactional, data could be file, or data could be stream kind of data, and there are tools for that. And then for storage, we looked at your storage has different options because you could be using caching data, you could be using search data, file store data, relational store data, NoSQL kind of data, data warehousing kind of data, or file kind of data, and there are storage options for that. Then we looked at processing part of the pipeline. We said that there are two kinds of frameworks. There is batch processing that you do with things like Redshift or EMR, and there are stream processing that you do with things like Storm, Apache Storm, or with Kinesis client libraries. And finally, we have the visualization buckets, and there are lots of tools in that ecosystem, BI tools, that you can also leverage. So I'm going to skip this. This is what my demo is. We are going to go to Marco and come back to it in the end if we have time.
Thanks, KD. Yeah, thanks, KD, for that. So, so actually, KD asked me to give you a kind of real life example of what I'm doing. So I'm running the aviation analysis department in the International Civil Aviation Organization. So the example I will give you, it's about accident things, But if you hear about ICAO, it's like accidents are really kind of rare events nowadays, But if something happens now, it's kind of exceptional, Like there's a plane lost somewhere in the Pacific. Okay, people ask themselves, okay, how is it possible we cannot find that plane? Okay, ICAO gets then into place, and so for those who know us, I'm from Montreal, and we are using AWS now in the cloud for maybe 6 years now. And we have different offices around the world, so different what we call regional offices. So since we use the Amazon cloud, everything has come really faster. So our office, for example, in Thailand, when they access our data and our analysis, I mean, everything has become much faster than before, where everything was stored in Montreal and people had to connect to it and all of this. So to go a little bit about the cloud, so what we think is that if the data we produce, it's really just meant to be used inside our organization, but generally we would prefer keeping it. Let's say our finance things, human resource stuff, medical things. So, but it's meant to be shared, so distributed. Well, we definitely put it on the cloud, but if it's collected internally, we try to kind of synchronize. And I'll give you an example of this. And because KD actually very much said it, all is about collection, storage, analysis, and visualization. Okay? So, and the collection piece actually very much starts, like for my organization, it starts with the person who gets something, puts something from paper maybe into a database. You know? And I think everybody of you has probably someone like that. Okay? So these people are using something which is very often not very fancy, and but which works. Okay, it can be local. They don't need to access it from their iPad when they're on the train. Okay, so on the other side, you have people who are looking at data, who are looking at metrics, at graphs. Well, those ones, they must have access to it from anywhere, from any device, and yeah, from the iPad on the train. But it's not the same people, so we try to segregate those. And when I talk analysis, I talk what is there on the right side. Okay, what's on the left side is part of the collection piece. So that can be very old, very whatever. I don't touch it. Okay. So I think you have pieces like that in your building. You know, when you think, oh, this guy, he's working on an old database. Maybe we can put that in the cloud. You just forget it. Okay. He knows how it works. Just leave it. Okay. Just get the data. Just get what you need, and then you do something with it. So I'll give you an example here of a MapReduce job we run every night in Akeo. So the idea was we had a few years ago is that why would we not build something really real-time? Well, real-time for an organization like mine is daily. Okay, it's not by the minute, but daily. That's for an international organization, it's kind of almost real-time. You know, it's like spooky stuff. If you're used to publishing reports once a year, okay, so something every day, that's already real-time. So we wanted to put data on accidents together. So we wanted to have every morning an aggregated set of what happened yesterday and all the information we can have on what happened yesterday. You know, we want to have it on our screens when we get in the morning. So at the end of the day, we are producing a page which looks like this. So this is now an example of an accident of some Fokker 50 which happened in Somalia. And we have like four sources of information for this. You know, so there are data we buy, or there are some geeks around the world who run a database, which is actually very good, but it's still not perfect. Okay, so we connect to that database, and then we collect stuff from there. So all the work we have to do is actually put all these different pieces together and see what is double and calculate some values, for example, categorizations. And yeah, we have to do that every day. Okay? And sometimes we're getting information we already had. So we have to know that, we have to identify those, and we have to replace it. Okay? So we use Elastic MapReduce for this. Turned actually out to be very useful. So first starting when we are getting the collection of the data. You will see if you have already done this, if you ask someone, okay, you send me your data, well, they will not send you the data as the other guy who just asked, okay? They're all different. So for example, we're getting data in an XML format from one of our sources and in a CSV format from another one, okay? When I want to use EMR likes when the data is in a line, and it can be any kind of format, but it has to be in a line. XML files are generally not in a line, okay? And the CSV files generally have a header, okay? So you have to get rid of that header because EMR doesn't know what to do with that, okay? So that means that we have to sort of pre-treating things. So when we collect in our collection process, so we connect to these different sources, and we're just running a small script, and the script identifies, okay, what's kind of the format of this? And then we put everything in a line format, okay? So that it can be ingested by EMR, okay? And very often the people think, oh, that's not useful. Well, very often when you get the data, you will see that that's not exactly how EMR will take it, okay? So we pre-process it, and then we put it into S3. So what is in S3 is per line. It can be like XML snippet or CSV kind of things, but EMR will take care of that, but must be in a line. So at the end of the day, we have a combined file, a kind of a huge file with anything which came from different sources and different formats. And so we're launching our EMR. And it's really easy, just like a scripting line like this. I'm just highlighted something because we are not, I'm a kind of I'm a JavaScript guy, okay? Maybe some people still think that's not programming language, okay? But for me, it's a programming language. I mean, I'm an engineer and I'm lazy by trade, okay? So if I can go around with one language, I do it, okay? And so JavaScript actually turned out to be very nice because I can use it for my client side, my backend, and I even have a database that runs with JavaScript, which is MongoDB, okay? So I'm using MongoDB. So to shuffle my results from EMR into MongoDB, I need to have a connection. So, and that's why EMR is actually very nice, so I can give it my key. So I have to send it my key, and EMR connects them to my database and puts the stuff there. Yeah, so this is the configuration file just to show you that it's really not very difficult. So you just define the steps, what do you want to do. So I'm having my input files, and at the end, when everything's finished, I tell EMR, okay, you have everything there, and then just shovel it into my Mongo database. Right? Because I gave it the key to it, so it's fine. So all of that is just like this configurations on some sort of Linux server. So my mapper, what is my mapper doing? Well, as an input, he gets a bunch of lines which are different formats. So some has a certain number of fields, the other one coming from another source, the fields are different. So the mapper has to find out first, so again, you see it's JavaScript. I already told you I like that. So mappers, I can write them in JavaScript. So I do that. So here I'm going through all the lines, and then I see, okay, what is it? Is it XML, or what is it? Is it CSV, or JSON, or whatever? And then I pick out the values I want to keep. For example, the model of the plane, the date where the accident happened, the location, and a certain number of fields I want. Sometimes the source didn't provide me that information, so I will not take it. Okay? So at the end of this, and KD actually mentioned it, it's all about the key. Okay? It's in key store, so we have to build the key. And the key for me is the registration number and the date. Okay? It's actually, maybe it has happened once in the last 50 years. I've seen it once, the same plane having 2 accidents the same day. Okay? Well, I think I'm able to filter that out manually, okay? So I think for this example, and it actually worked fine for now, and they're saying that the same plane has 1 accident per day. So that worked fine. So it actually simplifies my key thing here, okay? But I agree with you that if that would not be the case, I would have a problem, okay? Anyway, for now, that's fine, okay? So that's my key. Once I'm getting into my reducer, my reducer takes everything and then will put all the keys together. So why would I find different entries if I say that there's only one accident per day? Well, the thing is that I have my different sources, and they all gave me the information on that same thing. Okay, so I will have 3 or 4 or maybe 2 sets of information on the same event. So the reducer will put them together for me, and then I will just need to take decisions on who I will choose, and do my calculations. For example, using the registration number, I'm able to find the country through some mappings. And I'm also calculating some weights and different things. So that's all my reducer will do that. So at the end, I have a reduced data set with my values, and actually I have only kept exactly what I need to do my visualizations. And that's actually very powerful from the EMR point of view. It's that you can run those things, and you only keep what you really need at the end, okay? So for me, the visualization piece, or I call it publishing, but it's the same thing. So it's put into my MongoDB, and then with Node, which is well again JavaScript, I'm building APIs, which then feeding other JavaScript graphing tools, like for example I think the third one here is D3, the first one is R, and the other one are high charts. So that's all the JavaScript libraries. And so this is all on our websites, on the Archaeo websites. So every day These graphs, they are just connect to the cloud, to my node server, request the new data, and the data has been calculated overnight by my EMR job. And the servers for that are created and deleted when the job is finished, so I don't need to maintain anything. It just actually works. You know, and I think that's also what I like from all this. It just works. Huh? Okay, I think KD wanted to show you some other. Timmy, we have some time, huh? Doing an example. Thanks.
We don't really have any time.
No.
What I'm going to do is I'm going to play this. If you have to leave, please leave. If you want to ask any questions or see what the demo is about, please feel free to. I'm going to hang around for some time. Okay. So, oh, it already started. Thank you. So what's happening in this particular demo is we have public data sets in Amazon that are hosted for free in S3. One of those public data sets is the Wikipedia access data set. That data set tells us which Wikipedia page was accessed how many times in a particular day. All of that data is in S3. What I'm doing is bringing the data from S3 into EMR. When the data is in EMR, can you pause that real quick, please? I'm going to start it again shortly. Once the data is in EMR, there is a tool called Hive. Hive makes EMR or Hadoop distributed file system backend store look like a sequential store. So you can write some SQL queries on it. That Wikipedia log access data is missing the date piece as part of the data set. That's just missing. So using Hive, I am now inserting that piece of information back into my data store and then storing it. And once that data is put back in, all of that new data with this missing piece is brought into Redshift. From Redshift, I'm now using Pentaho to visualize the data. So, you know, the 4 steps here are ingestion of data from S3 into Redshift, and then there is processing of inserting more data using Hive into that data store, and then I store it back in EMR. After that, I am again ingesting that data from EMR into now Redshift, and Redshift is analyzing that data, and for visualization, I'm using Pentaho. So that's the 4 steps here. And in this video, I'm showing you all of these components one by one. So if we play that video again. Initially what I saw in this, you saw in this video is I went to the AWS Management Console, which is like your control room for Amazon Cloud. All your services are laid down there. I went to the EMR service. I showed that it's easy to resize EMR, and then there is a tool called Hue. Hue is a visual UI tool that EMR provides, or it's a tool in the ecosystem that lets you do things on EMR cluster using a graphical interface. I showed Hue, it's already gone, but Hue showed you how to write Hive queries and execute high SQL queries directly. After that, I'm showing that when you launch a Redshift cluster, Redshift gives you SQL functionality. So you can use your SQL tools, like I'm using SQL Workbench right here. Many of you are familiar with it. SQL Workbench can now interface with Redshift directly. And this right here is the Pentaho BI tool. I just started using it. It's very easy to use, but you can use others as well. In here, I am using it has many different components, but the 2 I used were called data integration, which lets you write ETL pipelines on your data sitting in Redshift from Pentaho. So that's the first one. In doing ETL, you have to specify the source of your data, the transformation on that data, and then the output part of the data. So those are the 3 stages. This is Pentaho's standard functionality. This is their community edition, which is open source. I'm using that to get data from Redshift, transform it by replacing some string, and then writing back to S3. This is just an example. I'm not going to execute it. But the bottom line is this data integration tool can let me transform my data very easily. And after this is done, what I'm going to show is there is a tool called report generator within Pentaho. Report generator lets you create reports that you can leverage, in your day-to-day work. The report that I'm generating gives me a bar chart, this is something that's already been done. So it shows you the graphs, and you can export it as PDFs and use it. Or you can create new reports by selecting the charts, etc. So that's all I had. I'm happy to answer any questions. I'll be hanging around, but thank you for your time.